Can you calculate a wait time accurately with computer vision in live video streams? Most tutorials make it look easy, but there's a hidden trap. Today, I'll show you the difference between analyzing static video files and real-time streams and how to build a solution that actually works in real world. The problem with tutorials is that they often oversimplify things. They use pre-recorded videos where you have perfect control over the timing and frame rate. Real-life live streams are messy. Frame rates fluctuate, and if your model can't keep up, your time calculation is useless. Let me explain. First thing first, let's talk about running the inference and calculating the time using static video files. The FPS of static video file is constant, and we can leverage this to calculate the time. We simply count the number of frames that have elapsed and divide the result by the constant FPS. It doesn't matter how fast your model is, you'll still get accurate time measurements. The only consideration is that the speed of the model will impact the total processing time. For example, if your model processes 15 frames per second and FPS of your video is 30, processing the video will take twice as long as the video's duration. On the other hand, if you can process, for example, 60 frames per second, it will take half as long. Now, let's talk about streams. Here the situation is much more complex. There are two FPS values that we need to consider: the FPS of the stream and the FPS of the model. If the FPS of the model is higher than the FPS of the stream, everything is fine. Our processing speed is simply bound by stream's FPS. However, if our model runs slower than the stream, then we have a problem. When our stream is decoded, all those frames land in the buffer, and our model pulls frames from this buffer in first in, first out order. This means if our model is too slow, we are pulling frames from the buffer slower than they are being added. This leads to two unwanted results. First, our latency continuously grows. We are no longer processing in real time. In reality, we process the video that was streamed further and further in the past. The second and more drastic issue is that the buffer storing frames continuously expand, and when it reaches its limit, our application will simply crash. To combat this problem, we can implement a feedback loop that measures how quickly AI model consumes frames and then limits the amount of decoded frames that make it into the buffer. Ideally, the code for decoding frames and the code for running the model should operate in separate threads, making it significantly more complex to implement. But today I'll show you how to do this with relatively low effort, even if you want to run multiple streams all at once. Some of you probably have a question. Why can't we just drop the excess frames on the model side? Simply pull frames from the buffer until it's completely empty. We could do this, and it would be probably a lot easier to implement. However, it's not the optimal solution. You see, decoding the frames is compute heavy. On weaker devices such as Jetson Nano, decoding a high-resolution stream like 4K can consume all the resources we have. That's why discarding the frames after they have been decoded is simply wasteful. It's much more efficient to skip the decoding entirely. Now that we can guarantee frames are processed with low and, most importantly, consistent latency, we can develop a strategy for calculating time for streams. Instead of relying on FPS as before, we'll use system time. Each time an object enters a zone, we will record the entry time, and with every frame, we'll simply subtract the entry time from the current time to calculate the duration of stay in zone. Based on what we've just learned, I created two timers: the FPS-based timer that we'll use to process static files, and the clock-based timer that we'll use for streams. Let's take a look at the implementation, starting with FPS-based timer. The code is quite simple. In the constructor, I provide information about constant FPS value. Additionally, two fields are initialized: frame ID storing the current frame number and tracker ID to frame ID mapping. The tick method increments the frame ID value. Additionally, the state of tracker ID to frame ID dict is updated by adding previously unseen tracker IDs. The last element is to calculate the time for each tracker ID visible on the current frame. To do this, we simply subtract the frame number when we first saw the object from the current frame number and divide the result by FPS to get the elapsed time in seconds. The clock-based timer is even simpler. Similar to FPS-based timer, a dict is initialized in the constructor, but this time it maps tracker ID to start time. In the tick method, we fetch the current time from system clock and update the tracker ID to start time dict by adding previously unseen tracker IDs. Finally, we simply subtract start time from current time to calculate elapsed time. Now, let's write some code and put our timers to the test. I know, it's all very complicated. Trust me, that's probably the most complex video I ever recorded. Fortunately, with every YouTube video, we now organized a community session, a live stream where you have an opportunity to ask questions and I do my best to answer them. So if anything in this video, the code, the examples, or my explanation is unclear, make sure to leave your questions in the comments below, or even better, join our next community session. The details about the date and time of the next session are in the description below. See you there. To set up the project, we will follow instructions from time in zone example in Supervision repository. The link to that example is in the description below. There are only few commands that we need to execute. We start by cloning the entire Supervision repository. Then we navigate to the directory containing time in zone example. Optionally, you can create and activate Python environment, which I highly recommend doing. It helps to keep your dependencies organized. Then we install all required dependencies specified in requirements.txt file. The two core dependencies we will use today are Supervision, a computer vision Swiss Army knife, which we will use, among other things, to filter detections by class and by zone, as well as to annotate them on the result frames. And the inference package, which we will use to run an object detection model locally and consume video streams. Inference recently added tools that enable easy and efficient processing of streams, even multiple in parallel. At this point, we are pretty much ready to go. The last thing we need to do is download an example video file. I had to make quite an effort to find a video that would serve as a good example for calculate time and zone, and I found a perfect video on YouTube showcasing a feed from CCTV camera in store. To download it, we will use one of the scripts. We only need to specify the URL of the video, the target directory, and the name of the target file. Finally, we are ready to jump into the editor and write some code. We will start by implementing the time and zone solution for static video files and gradually change the code to allow the same for video streams. Here's an almost empty Python file. Currently, the only thing there is a boilerplate code that allows me to parse arguments and a main function where I intend to implement our demo. We'll start by loading the model and visualizing detection results. To do this, we'll use the previously mentioned supervision and inference packages. Let's add the appropriate imports at the top of the file. Then, in the main function, we will use the getModel function to instantiate the model by passing the appropriate model ID. Model ID is a string that uniquely identifies each model on RoboFlow Universe. In my case, I'm using YOLO V8 weights pre-trained on Coco dataset. You can find a link to the dataset and the model in the description below. We need a way to process our source video. We'll use frame generator, which takes the path to the video file and allow us to iterate over its frames. Now we can simply use for loop to process the source video. Inside the loop, we will push our frames through model infer method. While doing this, we can define additional parameters such as confidence threshold and IOU threshold. Let's create an appropriate constants at the top of the file and set their value to 0.5. You can adjust them accordingly to fit your use case. Now we can pass those values as arguments. Let's break the long line into several short ones. Below, we can convert the output of our model into detections object, enabling us to utilize all tools available in supervision, such as annotators and trackers. Speaking of annotators, let's use one of them to visualize our results. Simply initialize the annotator and use it to draw our detections inside the for loop. Finally, we just use OpenCV to display the annotated frame on the screen and add a simple mechanism using keyboard interrupt to kill the script. We can see that the model successfully detects all people in the video, but occasionally it also detects a computer screen, tie of one of the clients, and a part of a checkout in bottom left section of the frame. The last one is quite weird. Let's try to fix it. I start by adding label annotator. We'll use it to display additional information about detected objects, such as their class, tracker ID, or later the time they spent in the zone. Let's add label annotator annotate call into the for loop as well. By the way, supervision has many other annotators that you can combine and customize. You can learn how to use them from the guide available in the description below. Next, we will initialize our tracker, which we will use inside the for loop to update our detections object, enriching it with tracker IDs. At the same time, we'll filter our detections to leave only those with class ID equal to 0. 0 is the ID for the person class in Coco dataset. Finally, we will define custom labels that we will pass to the label annotator annotate call. For now, let's just display the tracker ID for each detection visible on the video. Here's the result. We have successfully filtered out objects belonging to other classes, leaving only people. Both the detections and tracker IDs appear to be stable. A potential red flag would be if our detections flickered, resulting in random changes in tracker IDs, but it seems that in our case everything is alright. Let's move forward and add zones for every checkout lane and keep only those detections that are in zones. Every time I showed zone analysis in my videos, you ask me how to create your own zone configuration. This finally motivated me to create a small tool that you can run locally to design your own zones. Let's run it. We go back to terminal to run drawZones.py script, passing 2 arguments. We specify the source file, which can be either a photo or a video, and a target JSON location when we will save our configuration. Just remember, if you use a video, it must be recorded with stationary camera, so that the zones drawn for one selected frame apply to all of them. Defining the zone is very simple. Just click point by point, and when you are ready, click enter to accept the zone. If you want to abort drawing, simply press escape. Unfortunately, at the moment, the tool does not allow editing of an already defined zone. Finally, if you want to exit without saving, press Q, and if you want to save the results to target JSON file, press S. Now let me show you how to load this configuration and draw zones on the frame. We go back to the editor and import load zones config function at the top of the script. This straightforward function loads our JSON file and returns a list of NumPy arrays. Below I paste a color palette that I plan to use for drawing my zones. Then within the main function I called load zones config and assign the result to a variable named polygons. All we need to do now is loop over the polygons and use the draw polygon function available in supervision to draw each of them in different color on the output video frame. When we run the script, we see that the zones are now visible. It's time to filter out detections that are outside of the zones and mark the remaining ones with appropriate colors. By the way, if you're interested in learning more about zone analysis, on our channel we have a video where we took this concept to next level and demonstrated how to use it for analyzing vehicle flow at the intersection. Probably one of my best videos. To determine whether a given detection is inside or outside the zone, for each of polygons we need to create an instance of polygon zone. Apart from geometry definition, polygon zone requires information about the resolution of entire frame. To obtain this, we'll capture one of the frames from our frames generator, and then by analyzing the shape of NumPy array representing the frame, we'll calculate frame resolution. Now we can return to our list comprehension and pass it as a missing argument. Let's now modify our for loop to iterate over zones instead of polygons. Each of zones contain information about the associated polygon, so we can change this line as well. Now, using the zone trigger method, we can identify only those detections that are inside the zone. We just need to make sure that we are passing detections in zone and not detections object to our annotators, and that's it. We have successfully managed to detect, track, and filter our detections. Now we are finally ready to integrate our first timer. As mentioned earlier, for processing static files, we'll use FPS-based timer. Now let's add the appropriate import at the top of the file. Then, inside the main function, below definition of the zones, we create several timers, one for each zone. To initialize them, we need to know the FPS of our video. To extract it, we can use the supervision utility called video info. Now we can simply create multiple timers using list comprehension. Let's scroll down to the nested for loop and calculate how long each object spent in the respective zone. We can now display the information using label annotator. Instead of looping only through tracker ID, let's use zip to iterate simultaneously over tracker ID and time and zones. Finally, we update our string formatting and we are ready to see the result. Great! It seems that our FPS-based timer have correctly calculated the time. Remember, this timer leverages constant FPS. It counts how many frames have passed and divides this value by the FPS. And that's why we cannot use this strategy by processing streams. There is simply no constant FPS. Now, let's reorganize our script and try a naive way of processing streams and calculating the time. Here, the model will simply pick every frame from the buffer without any feedback loop that would limit frame production. On top of that, FPS of our model is lower than the FPS of our stream, which will cause the problem. Let's start by changing the list of arguments accepted by the script. We will no longer be consuming a static file, but a video stream instead. We removed the source video path argument and replaced it with RTPS URL. Similar changes are also made to the main function. Next, we import the getStreamFramesGenerator function, which, just like getVideoFramesGenerator, will allow us to iterate through our input frames using the for loop. Now we just need to use this function to initialize our frame generator, and just like that, we can consume a stream instead of video file. The second change we need to make is to switch from FPS-based timer to clock-based timer. We update our import and initialize timers in the main function. Now we no longer need FPS. Now, to test our code, we will need RTSP stream. Of course, if you have one, use it, but since I don't have any, I will use a different trick. I prepared another script that allows me to locally stream a video file. It pretty much takes the file from your hard drive and stream it over RTSP. This is perfect because it allows us to easily compare the result between static video file and stream processing. The script can stream multiple videos locally at once, but we only need one. We just pass the directory containing our video and the information that we need only one concurrent stream. Then press enter and it goes. By the way, the script requires you to have Docker installed. We can open a separate terminal tab and run docker ps there to confirm that the RTPS server is streaming. A good way to test if you have access to the source stream is to use VLC. Click on the file and from the drop-down menu select Open Network. Now you just have to enter the address of your stream. I copied mine from the terminal, click Open, and that's it. If the stream is available, it will be displayed on the screen. Now it's time to test our code. On the screen you see two clients consuming the same stream. The one on the top left corner is VLC, which displays the stream generated by our script with negligible latency. And on the other hand, the one in bottom right corner is our time and zone app. The source stream flows at about 15 FPS. As shown by the FPS counter of our app, it is running at about 9 to 10 frames per second. We see how over time the difference between both clients increases. As I mentioned in the introduction, this happens because our model can't keep up with processing all the frames that entered the buffer, which leads to latency growth and ultimately to a crash of our application. Now it's time to use Inference Pipeline to fix this problem. Inference Pipeline is one of utilities available in Inference package that, among other things, help us with efficient processing of video streams. It divides the processing into several threads and takes care of communication between them. All we need to do is provide the model ID and the callback that we wish to execute on every frame of our stream, and that's it. This, however, will require a major refactor of our code, but believe me, it's still much easier than writing all that thread communication code on your own. We start by importing Inference Pipeline and video frame classes at the top of the script. Next, we'll define a custom sync class with, for now, empty constructor and onPrediction method. That's the method that we will pass to Inference Pipeline, and it will be executed for each frame picked from the buffer. Most of the code we need is already written, we just need to organize it. Now let's start by initializing our tracker, polygons, and timers in the constructor. Zones cannot be initialized yet, as we need to know the frame resolution to do that, so for now let's use none. Then we need to add self in all appropriate places so that all these variables became class fields, and ensure that zone configuration path is provided through the constructor. Now let's focus on onPrediction method. The first thing we need to do is to initialize zones. So we verify if self zones is none, and if so, we calculate the frame resolution and assign a new value to our self zones. Now we copy most of the code that processes a single frame, all the tracking, filtering by class and by zone, and of course annotation, and paste it into onPrediction. We just need to remember to make few minor adjustments, primarily adding self in all appropriate places. Finally, we can remove all the remaining content of the main function and replace it with implementation based on Inference Pipeline. We begin by initializing custom sync. We must remember to pass the zone configuration path as an argument. Next, we create our pipeline. We pass the model ID, the address of the stream, and the onPrediction callback as arguments, and start the pipeline by calling the start method. Let's take a look at the final result. Again, we have two clients consuming the same stream. The top left is VLC and the bottom right is our time and zone app. The stream still has 15 FPS and the script consumes about 10. Despite this, latency doesn't accumulate because some frames are dropped, allowing for stable processing. This enables our timer to correctly count the time. Before we wrap it up, let's talk about important considerations that might impact the quality of your results. First of all, as I mentioned during drawing the zones, the camera we are going to use needs to be stationary. There should be no zooming or panning. Otherwise, the zone we draw will no longer be accurate. But the camera angle is just as important. Now take a look here. This is the camera feed that looks at the same checkout lane. However, you can immediately see that designing a similar solution for this camera would be much more difficult. It's quite hard to assign specific detections to specific checkout lanes because people and lanes occlude each other. To summarize, choosing the right camera angle is critical, and doing it right is part of designing a good computer vision solution. Some of you probably noticed that the stability of detections got worse when we switched from processing static files to streams. That's because of degraded image quality caused by real-time compression and unstable network connection, which makes it harder for the detector to identify the objects we are looking for. Problems with detection quality can ultimately lead to loss of tracker ID and consequently to timer reset or swap. Therefore, it's crucial to test the model on target hardware and in conditions as close as possible to those that we expect on production to ensure that the model will be able to successfully detect objects. There are also tools such as active learning offered by the inference package that help you detect changes in model behavior between the test and production environments. Whew, we learned a lot today. Not just about calculating time, object span and zones, but also about the differences between processing static files and video streams. This video was certainly one of the most challenging ones I made so far, and I really hope you like it. If you have any questions, make sure to leave them in the comments and I'll try to respond to all of them during the upcoming community session. Make sure to check out our open source projects like Supervision, Inference, and Autodistill. And spoiler alert, we are cooking something new for you. If you liked the video, make sure to like and subscribe and stay tuned for more computer vision content coming to this channel soon. My name is Peter and I'll see you next time. Bye.